Alright guys, hope everybody is staying warm. Uh, Wanted to go ahead and get this video recorded so that you have plenty of time to watch it and take notes and do the readings that you need to do. I've got a couple housekeeping slides here. I just want to remind everybody that test 1, the window opens up on Monday morning and closes Wednesday evening. So you have 3 days to take that test. If you don't know where the computer testing center is, we will go over that in class on Monday morning. Also, quick reminder that test prep quiz 1 is going to be due Wednesday evening, so you want to make sure that you do that. You can take that test prep quiz as many times as you'd like. I recommend that you take it, that you go back and see what you missed, that you look those things up, retake it, keep doing that until you get a good grade on it. It will help you significantly with the actual test. All right, we are going to pick up where we left off last class, which is we're going to start talking about the cerebral cortex. So the cerebral cortex is usually what you think of when you think about the brain. Kind of looks like worms. It's kind of weird looking. But this is a little different than what we've been talking about so far. So far, all the parts that we've been talking about are mostly on the inside of the brain. This is on the outside of the brain. So the outside area is mostly called the cerebral cortex, and it has a completely different set of functions than all the parts that we've been talking about before. So let's get into that. When we talk about the cerebral cortex, we are going to have to discuss a few different concepts here. The first one is that the cerebral cortex is made up of interconnected neural cells, and they cover the brain, and they kind of what the slide says, it covers the cerebral hemispheres. There's two halves of the brain. There's a left half and a right half. And the cerebral cortex kind of is our ultimate control and information processing center. It is it's kind of where the magic happens. It's where we think consciously about things. So this is what separates kind of higher level animals from lower level animals. The cerebral cortex is made up of a lot of different sections. We're going to cover kind of 4 main lobes. If you want an easy way to think of the lobes, you can think FPOT, which is an acronym, and it goes for the frontal lobes, which is the F, which those lobes primarily handles speaking, planning, judgment. They include the motor cortex, which is kind of that dark pink part. So the frontal lobes are the pink part. The dark pink part is the motor cortex, and the motor cortex handles sending information to our muscles to make decisive movements. Next is the parietal lobes. Those are the yellow part. These basically handle sensory input, touch and body position. They include the sensory cortex, and those, like I said, they handle all the things that we feel and that sort of thing. They process information that gives us spatial awareness, helps us sense things and that sort of thing. Next is the occipital lobes. Those are in the very back there. They're that little green spot. The occipital lobes include the visual cortex. They where our eyes connect kind of directly to the occipital lobe. And the occipital lobe is so connected to your vision that in cartoons, when people get hit on the back of the head and they see stars, that can actually really happen, because when you get hit on the back of the head, that traumatizes the occipital lobe. And so that is why if you've ever been hit really hard in the back of the head and you saw stars, that's why, because it traumatized your occipital lobe a little bit, and that was kind of your brain's response. And then the last one are the temporal lobes. Those are kind of right behind the temple. Those also handle auditory input. So everything that we hear, those kind of exist right above the ears, which makes sense from kind of an evolutionary standpoint. So, information doesn't have to travel super far in order to be processed. So here's another picture kind of the lobes. Remember, it says FPOT. So see here, we've got the frontal, parietal, occipital, and temporal lobes. So you remember that with FPOT. That helps you remember the lobes. Also, you can see from this picture that if we do a cutaway of the brain, that it has two kind of mirror images of itself, and those are the hemispheres. So the hemisphere on the right side of your brain is the right hemisphere, and the hemisphere on the left side of your brain is the left hemisphere. Got another picture here that kind of demonstrates where the auditory cortex and the visual cortexes are. Again, your auditory cortex is right there by your ears. Your visual cortex is in the back of your head, which I don't know that we have a firm understanding of why it's in the back of your head. From an evolutionary standpoint, it kind of seems far away, but it is a straight shot, so maybe that has something to do with it. It's a straight shot from your eyes to your visual cortex. All right, so talking about sensory and motor cortices, which or cortexes, depending on how you like to pronounce that. For both, the neurons are dedicated to, the neurons in each little spot there are dedicated to what parts of the body they control. So you can see up here at the top of this picture is like the hip and the knee and the ankle and the toes. And then it kind of, as we work our way from the top of the brain kind of towards the outside of the brain, you can see that it goes to the arm and the wrist and the fingers and the thumb and the neck and the brow and the eye and the face, and so on and so forth. So what they have found is that there are actual like sections of cells that are dedicated to controlling each portion there. And so the cells that control your ankle are going to be different from the cells that control your eyes, so on and so forth. So, and then again, for the sensory cortex, they function kind of in the same way, only they are taking in information rather than putting out information. And those are so close together because, as we talked about in our last class, that creates kind of that feedback loop. So when you reach out, your motor cortex is telling your hand to reach towards your coffee cup, and your sensory cortex is sensing where in space that hand is. It feels when your hand touches your cup, and it tells your brain that your hand is touching the cup, and then your motor cortex tells your hand to pull tight around that cup. You're able to pick it up and move it to your face and take a drink. If you have a breakdown in that process, that's when you knock over your coffee cup and make a big mess. And those are so close together because they need to do that feedback loop. So let's talk about some association areas of the brain. Association areas are areas of the cerebral cortex that are not involved in primary motor or sensory functions. Those are what are responsible for our ability to learn, our ability to think and speak and remember things, our ability to kind of have those like meaningful cognitive thoughts. So if we look at these different animals that are kind of different levels of processing, we have a rat. Almost half of its brain is motor areas and the other half is sensory areas. If we have a cat has slightly bigger motor area even than a rat, although it's a much smaller percentage of its brain. And then you can see there it has a very small association area. Moving on to a chimpanzee, chimpanzees have bigger motor and sensory areas than a cat or a rat, but they're a relatively small amount of their brain as far as a ratio goes. A chimpanzee has more association areas, has more ability to learn and think and remember things. And then you look at a human, has the largest motor and sensory areas, but also the smallest ratio. It definitely has the most association areas. So that is why we are able to learn and remember and think and speak at a higher level than other animals. For the next part, we're going to look at kind of a case study. It's a pretty famous case study of a guy named Phineas Gage. And when we talk about Phineas Gage, we're going to talk about one of the most important association areas in the brain, which is the frontal lobe. And the frontal lobe is linked to different functions. Those involve intelligence, memory, planning. There's also some evidence that it's linked to judgment and things like that. So we've talked about what the average brain looks like, but what happens if it's damaged or altered in some way? That's kind of what we're going to explore with the story of Phineas Gage. So with Phineas Gage, in 1848, he was kind of a management level, like a middle management guy, working in the mining industry. And he was one of the things they did was they in order to create explosions, they would drill a hole down in the ground and they would fill it with gunpowder. And then they would tamp down that gunpowder, which means kind of pack it tight with a big metal rod. For some reason, Phineas Gage was tamping down some gunpowder into a hole, and the gunpowder ignited. So maybe his metal rod like hit a rock and created a spark. They don't really know, but the rod shot up into the air. As it shot into the air, it passed through his occipital area, which is like through his eye, kind of right behind his eye. It took out his eye, passed up through his brain, and out his skull on the other side. So you can see there on the right hand side, or on the left hand side, is kind of an example of what it did. And on the right hand side is Phineas Gage's actual skull. Now, as a result, Phineas Gage's memory and intellect remained intact, but he was never the same, as you can probably imagine. Prior to this, he had been friendly, he was soft-spoken, he was well-liked, respected member of the community. But after the accident, he was crude, he was irritable, he used a lot of profanity, which was not like him, and he was dishonest and impulsive. So this accident really had a major impact on Phineas Gage, not just on him medically, but on him as a person, as a human. It changed who he was. So why did that happen? Well, there's some things that we need to understand about the brain before we can really understand why that happened to Phineas Gage. So we're going to talk about a brain hemispherectomy, because kind of prior to Phineas Gage, there was this thought that if something happened to your brain, you just died. And Phineas Gage, he didn't die. As a matter of fact, the story goes that he went home and they called the doctor, and when the doctor came, the doctor didn't believe that what he said had happened until he sneezed and some bits of his brain came out. And then the doctor was like, oh my gosh, like, this is for real. So with this understanding that you could have major damage to different parts of your brain and survive, there came to be this curiosity about how can we use this information to help people. How can we use it medically? And so they found that the brain is what they call high in plasticity, which means that it's able to adapt and adjust. When something like what happened to Phineas Gage happens, the remaining brain takes over for the damaged part of the brain. This understanding led them to start trying to do a thing called a brain hemispherectomy. which is where they make an incision in the skull and kind of remove a piece of the skull. And then a surgeon goes in and possibly removes some parts of the brain, and they disconnect some other parts. And one of those things is the corpus callosum, which we'll talk about in just a minute. But then at the end of the procedure, they put the skull back in place and they stitch everything back up. And they do this typically to children who are experiencing major problems like seizures. And what's amazing about this is that brain plasticity allows the brain to change and adapt, and the child who this happens to, they're able to, maybe we'll say, stop seizures, and the brain then kind of recreates some of those neural networks, or those roads and paths and highways that we talked about in the last class. They're able to continue to function. So we see this also in things like blindness, right? So somebody loses their ability to see, and their sensory cortex kind of offsets that with giving them more sensitive touch, which is how blind people are able to read Braille. And it helps them hear very well. Typically, blind people have better hearing than seeing people. They're able to have a better sense of kind of their space in the world, because their brain is adapting for them. And their sensory cortex is picking up in other areas where it struggled before. So one of the other things is that the brain, they've found that the brain is more plastic with children, and this is largely has to do with neurogenesis, which is the brain's ability to create new cells. Hemispherectomies in young children can lead to a pretty normal life, although there have been issues with paralysis to one side of the body. But for the most part, the brain is able to rebuild and readapt in a way that allows a child to grow up to be functional. So I mentioned the corpus callosum a little bit ago. This is kind of what the corpus callosum looks like. It is this big bundle of nerves that attach the right and left hemispheres of the brain and help them to communicate with each other. And we are going to actually watch a video together of a guy who, his name is Joe, and he had his corpus callosum surgically disconnected. So the right and left side of his brain, they don't communicate anymore. And we're going to look at a case study of how that has impacted his life. And I think you're going to find it relatively interesting. So without further ado, here's some information that I kind of said to you but didn't put up on the slides. So without further ado, let's watch the video, Our Divided Brain.
We began our journey into the human brain here on the campus of Dartmouth College in New Hampshire. I'd come to meet one of the world's leading brain scientists, Mike Gazzaniga, and a man he's worked with for over a decade. A man with two brains.
You've been working a long time with Dr. Gazzaniga?
14 or 15 years.
It doesn't seem like that long, does it?
The collaboration began when Joe had surgery.
And you had this procedure to correct an epileptic problem,
Yes.
Is that right?
Trying to stop the seizures. I was having seizures like every day or so, or sometimes 2 or 3 a day.
To control Joe's epileptic seizures, a surgeon severed the connection between the two halves of his brain. Cutting the corpus callosum like this prevented the spread of the electric storms that caused his seizures. But it also prevented the left and right halves of his brain from communicating with each other. In the years since the operation, Joe's epilepsy has been under control. He now earns a living at an egg farm, And in his everyday life, he's largely unaffected by the fact that his left and his right brains work independently.
Do you feel any different when you think about something than you did any differently from the way you felt before the procedure?
It's just got a backup brain, that's all.
That's something everybody could use, right?
I found out how true that was right away when I was asked to draw a different shape with each hand. In a brain like mine, roughly speaking normal, at least all in one piece, the left half of my brain controls the right side of my body, while the right brain controls the left side.
Oh, no.
But because the two halves are connected,
Nothing wrong with that.
getting each hand to work independently isn't easy.
Well, we're seeing the fact that that Alan's hemispheres are connected, and that the motor messages from one are confusing the motor messages in the other.
I was just drawing an upside-down duck.
Okay.
But when Joe is given the same task, his two hands operate as if controlled by two separate brains. What's happening is that each half of Joe's brain is given a separate instruction. He's asked to fix his eyes on the cross in the center of the screen. Anything flashed to the right of the cross goes only to his left hemisphere. Things to the left go to his right hemisphere. Because the two don't communicate, each hand does only what its half of the brain sees.
Wow, look at that. It's really like two different people doing the same.
That's right.
Same task.
That's the idea.
Okay, Joe, I want you to keep your hands out in front
In
of
an
you.
experiment that's now a classic in brain research,
Hemisphere.
Mike Kazaniga over 30 years ago used a similar setup to find out if the two halves of the brain are specialized to do different things.
Ship.
Joe is being flashed a word only to one half of his brain. Words flashed to the right
Storm.
are seen only by his left brain, and Joe can report seeing those words just fine.
Piano.
Good.
But when a word is flashed to his right brain,
Didn't see that.
Okay. Joe, I'm going to ask you
but now watch what happens.
to draw that with your left hand.
You get me lost.
Why don't you try drawing another picture of it over here if that will help you.
Oh, phone.
Oh, okay.
Durr.
It's almost as though somebody has given him a secret communication.
That's
and
right.
Now he knows that it's a telephone, but up until then he was blind to it.
Exactly.
When Gazaniga first did this experiment, it instantly proved that the ability to speak resides almost exclusively in the left hemisphere. Not until he sees what his right brain is drawing is Joe able to name
He
it.
said church, didn't he?
After looking at the picture.
But he had to figure it out about as long as we did. That's really interesting. It's a picture here of somebody communicating almost with another person.
And the communication is not occurring inside the head, it's occurring out on the piece of paper.
Yeah.
Blob. I really don't know.
You want to draw a little bit more?
So far, Joe has been seeing only one word.
Cat. That's a cat
Things get
sound.
even stranger when he's flashed two words, each to only one half of his brain.
The right hemisphere saw toad.
Yeah.
And so his left hand draws a toad.
So there's the toad.
Oh, it's a toad.
And this time I was able to guess what was coming.
Will they put a little three-legged stool in there later, or what?
Joe's speaking left brain saw a stool. Saying the word lets the hand that's controlled by his right brain in on the secret.
That's great. That's really interesting. And if he had seen that with the corpus callosum intact, he would have drawn a toadstool.
Right.
Not a toad and a stool.
Right, exactly the point. I've been doing this for 35 years. Yeah.
And
It gets me every time.
Yeah, it must. It must.
This time, instead of naming the word, I want you to point to the word.
Again, Joe sees two words simultaneously. Bell goes to his non-speaking right brain. Music to his speaking left brain. When asked to point to a picture of what he saw, he chooses Bell. But when asked why,
Okay, why'd you pick that one?
Use it.
Music?
and when asked to explain,
It was music and bell, and it was a few minutes ago. Last time I heard any music was coming from the bells out here,
Uh-huh.
banging away.
So the bell's
Yeah.
outside here.
So but good enough answer to me.
What's extraordinary is that Joe's speaking left brain concocts a plausible story of why he pointed the bell, even when some of the other pictures more obviously represent music. Gazzaniga believes this determination to find cause and effect, this desire to explain, is the left hemisphere's most marvelous property.
One of the unique things to the human brain is this need to interpret why two events occurred. What was the antecedent to this? What caused this? And if you can imagine that a species like us that has that little chip in its brain that asks those questions is going to survive rather well, because it's going to figure out more about the nature of the world than a species that doesn't have that.
Okay, Joe, I want you to keep your hand.
But as I was about to discover, the right brain has a very useful survival skill all its own.
What do you think will happen here?
So for you, we're doing a live experiment. Never done it before.
The experiment involves the 16th century Italian painter Arcimboldo, who made faces out of fruit, flowers, meat, even books. From other research, there's reason to believe that the ability to recognize faces is located exclusively in the right hemisphere. So Mike wondered if Arcimboldo's paintings would look different to each of Joe's two brains.
So will his left hemisphere say, I saw a potato, I didn't see a face? And will his right hemisphere say, I saw the face, and not comment on the fact it was made out of a potato?
You're going to see a figure followed by a choice of two words.
If this works, it'll be terrific, but we'll see. So here it is, live.
Okay?
The first painting goes to the right hemisphere. And Joe points to face. The next painting goes to his left brain. And this time he points to fruits. Mike seemed pleased.
Are you having a moment?
This is too good.
Again to the right brain, and Joe sees it as a face.
Point it down.
But to the left brain,
Face made out of books.
Point it up.
What are the books?
Are you happy with what you're
Fruit.
seeing?
It's unbelievable. He's doing it. You see that?
It's good. It's going so fast. It's shifting from left to right so fast. I can't keep up with you. You're used to looking at this.
When you show him a face in the right side, the left hemisphere,
Yeah.
he's focusing in on the elements that made up the face.
Yeah.
When you show him the exact same picture in the left field, going to the right hemisphere, he's focusing on the face and not the elements.
And not the elements. If you came down from another planet and you saw faces and vegetables, you might not think there was much of a difference among them. But the brain seems to be made up in a certain way to say faces are very different from other objects.
That's right.
And one side of the brain specializes in faces. huh?
Exactly right. Exactly right. It is an adaptation that we have to detect upright faces. It's a very important. You can imagine in an evolutionary time that all of a sudden you have the ability to detect quickly an upright face. You want to read the expression on that face. You want to know if it's friend or foe. You want to have a set of questions about that face.
the right brain might be skilled at recognizing faces. But when it comes to what gives the human mind its power, the ability to reason, to invent, to interpret the world around it, Mike Gazzaniga's 30 years of research has taught him which hemisphere he wouldn't want to be without.
The old phrase around our lab is, don't leave home without your left hemisphere. That's where the action is.
Here's a picture of kind of how that looks. This really does a good job of demonstrating that the left hemisphere processes the things on the right side, and the right hemisphere processes things on the left side. And this is what is known as, when you're doing it through the eyes, that's called visual crossover. So this happens visually, but it also happens with hearing and that sort of thing. So information that is taken in on the left side of our brain is actually processed by the right side of our brain, and information that is taken in on the left side of our body is processed on the right side of our brain. If you look at this picture, you see that the pencil on the left is going to be processed visually through the eye on the left, but that information is actually going to be processed and understood through the brain on the right-hand side. And the apple, which is on the right-hand side, is going to be taken in mostly by the right eye, but then it's going to be processed by the left hemisphere of the brain. So when we cut the corpus callosum, or corpus callosum, one of the benefits to that is that it eliminates seizures. Those seizures are caused by kind of over communication, we believe, in the brain between the two hemispheres. And when that happens, the visual crossover still occurs. The thalamus is still functioning. It's still sending that information to the other side. However, the hemisphere that processes it can't tell the other hemisphere what it has processed. And that leads to kind of that strange thing we saw where, he could draw a toad and draw a stool, but he couldn't come up with the word toadstool. Whereas, you and I might look at that and draw a mushroom because we recognize toadstool as one thing. He had to process it as two separate things. So here's how that experiment works. They have somebody look at the dot. They put something up on the screen. In this case, it's two words that spell the word heart, but they process them as he and art. They ask, what word did you see? She says art. They say, point with your left hand to the word you saw, and they point to he. Together, they could put together that they saw he and art, and that actually means heart, but somebody with their corpus callosum severed is going to have to kind of work that out, whereas our brains typically are going to process it instantaneously, and we're going to see the word heart. So that is where we're going to end our discussion about the brain, and we're going to switch gears here a little bit. We are going to switch to gender development, actually. We're going to jump to Module 14. So I hope you definitely read this section because it's important. Gender development is one of those things that is often very misunderstood. A lot of people have a lot of explanations for gender development, and we are just going to look at it kind of from the scientific standpoint. So, and from our understanding through social psychology and that sort of thing. So, everything that we look at is going to go back to this genderbread person here. We're going to use it to talk about the different dimensions of sex and gender development when we do both of them. But what is important to understand is that these happen kind of on a spectrum. So, men and women are not the opposite ends of a spectrum. We have a tendency to assume that they are, and that is what's known as gender polarization. And we also have a tendency to assume that there really are only two genders, male and female, man and woman. We kind of see them all as the same, and that is called a gender binary. But what we're going to see is that that's not actually how it works. So to see that, the first thing we're going to talk about is biological sex. So what's important to note about this is that when we talk about your sex, we are talking about your biology, about what your kind of DNA has decided that your sex will be. We're looking at male and female typically. However, there are times when somebody is either intersex or transsexual. So even something as simple as male and female are not quite as simple as we tend to think of it. But sex is biological, and it is always talking about a person's sexual organs, their hormones, their chromosomes. So we are not talking about whether or not this person wears a dress or pants or has long hair or short hair, whether or not they choose to participate in a combat sport or they like to cook. We are talking truly, when we talk about sex, we are talking about their biology. We are talking about whether or not they have a penis or a vagina, their hormone levels, and what their DNA says. So let's talk a little bit about how DNA determines sex. Um, in your book on pages 179 and 180, it talks about sex chromosomes. It's going to give you a little more information than I'm going to give you. But basically, what it boils down to is that your sex chromosomes determine your sexual characteristics. So females typically have two X chromosomes. Males typically have one X and one Y. Now that is not the only choices there are, but these are going to determine primary sex characteristics, what our reproductive capacities, what our sex organs are. They're going to influence whether we grow breasts or facial hair, how our pubic hair grows, whether or not we have an Adam's apple, that sort of thing. So they definitely contribute to the biological distinctions between sexes, and kind of help us to determine those physical characteristics that we attribute to male or female. But like I said, not everybody falls into the male or female role. Some people are what is called intersex, and these are people who maybe are born with, say, as an example, both testicles and a vagina. These people are typically some sort of combination between male and female. And what typically happens with an intersex person is that the doctor gets together with their parents and they just make a decision. Do we want this child to be male or female? And then they do they call it a corrective surgery, to really truly assign a binary sex at birth. The runner that you see right here, her name is Caster Semenya, I believe is how it's pronounced. She is an intersex athlete who did cause some controversy by competing as a woman, but for all intents and purposes, she is a woman. So people did have some problems with it because they said she's an intersex person. So I challenge you to think about sex as separate from gender, especially during this lecture and this discussion. But really, in your everyday life, we should separate those two things. Your biology doesn't necessarily determine everything, and we're going to see that a little bit more here. I've got a little cartoon here that says, "Have you ever noticed how ghosts look a lot like octopuses?" It's true. It's kind of like the similarity between most people's understanding of gender compared to what gender really is. Most people understand gender as a ghost. Gender is really like an octopus. You see, octopuses are complex creatures that scientists are still working to understand, and ghosts are inventions. So that all kind of demonstrates that psychologists are and scientists are, truly still trying to understand gender, and what it is that it's complicated. And this is typically what psychologists are interested in. We're not particularly interested in somebody's biological sex nearly as much as we are in their gender. So let's talk a little bit about what is gender. So gender is basically a way that we categorize people. Gender is not the only way we categorize people. Sometimes we also categorize people by race, by sexual orientation, by physical ability, by age. There's lots of different ways that we can categorize people. But one of the first ways that we categorize somebody, and we do this before they're even born, is we determine their gender. This is kind of a cultural thing, and it's important to know that different cultures make different associations between what it is to be male and female. But we look at this pretty much as soon as they're born or even before they're born, we decide whether or not they're going to be a man or a woman when they grow up. Gender is socially constructed, which means that by itself it has no meaning. It is something that we have assigned meaning to it, and it only means what we decide that it means. So different cultures have kind of different ideas of what it means to be a man and what it means to be a woman. But what's interesting is that that meaning that we have assigned it is so powerful that people who do not identify as strictly men or women are pathologized. We assume that there is something wrong with them, and we treat them as if something is wrong with them. So let's talk a little bit about gender expression. And the reason that we say expression is because gender expression is kind of how you show outwardly which gender you identify as. And so, are you going to be masculine or feminine? Are you going to be androgynous? Are you going to be gender neutral? Are you going to be hypermasculine? Gender expression is also kind of a social thing, and it is, again, determined by things like clothing choices, the way we speak and converse, and the way we behave. So, again, gender expression varies from society to society and culture to culture. So the social construction of gender roles, we generally speaking, we call that, or social construction of gender, we call it a gender role. And a gender role is going to be the expectations about how men and women should behave. So, we, with gender roles, we talk about how, historically in the U.S. and in Europe, women have expected to be subservient to their husbands, to take care of the home, to be seen and not heard, to cook and clean, to be beautiful, and to have and raise children. Whereas, men are expected to kind of be the opposite of those things. They're expected to be dominant. They are not expected to take care of the home, but maybe to fix things. They are expected to speak in a way that makes their presence known. They expect dinner at the table when they get home rather than expect to make it. They don't have the same beauty standards as women historically, and they generally have historically played a much smaller role in the raising of children. So gender roles, they are a form of gender expression. They are a response to expectations that are laid out there, and they start really, really early in life. You think about phrases like "man up" and "big boys don't cry," and then later on, we say that we don't expect women to be good at math. We don't expect them to be good at science. We expect men to take control, that sort of thing. So that's kind of how those expectations play out and are expressed. So I want to just kind of give you a second here to think about how the construction of gender really plays out. And we have some questions here. It says, think about it. Who initiates dates and sexual activity? Who is the primary breadwinner? Who takes care of children and housework? Who is supposed to worry about their appearance? Who is free to express a range of emotions? I want you to think about the consequences to these answers. What happens if men are taught that they should be sexually dominant? The answer to that is rape culture. What happens if women are taught they need to be beautiful in order to be valued? Some of the consequences might be objectification of women, eating disorders. What happens if men feel that they can't admit to being sad or hurt? The answer is that men are more likely to complete suicide. You see, even though strict gender roles tend to cause more harm than good, we still hold on to them. Now, that's not to say that masculinity or femininity are inherently bad or good. They kind of just are what they are. But it's the value that we place on these identities and how we act on them that is really what can cause harm. So let's talk about gender identity. We live in a culture where there are certain rules about how we act or perform our gender, and so we need to look at how does that contribute to how we identify. If we look at this picture, we see that typically we act out gender by identifying as woman or man, but that isn't kind of the limit to how people can identify or express themselves. And if you move those dots into different spots, you can see that somebody could identify as two-spirit or genderqueer or genderless or transgender. But how we identify is largely psychological, and it is kind of a person's sense of how male or female or whatever that they are. And so, some men identify really high on the manness side of things, while other men don't identify as super high in masculinity. Some guys are just, not as masculine as others, and the same goes for women. Some women are higher or lower on femininity and masculinity than others, and that's okay. We need to be, I think, a little more accepting of the way people express their gender and the way that they feel that they are defined by it. So, how does gender identity develop? One of the ways that we kind of explain gender identity development is through social learning theory. Social learning theory says that we learn gender roles because we observe the behavior of other people and then we imitate it. Also, it says that we are rewarded and punished for that. So an example of that would be, a little boy falls and scrapes up his knee. We don't coddle a little boy the same way that we would coddle a little girl typically. So a little boy falls and scrapes his knee and starts crying, and you tell him to stop being a sissy. A little girl scrapes her knee and starts crying, and typically you're going to be more comforting to her. So we give subtle messages. Young girls speak quieter. They value being neat over being creative. They value appearance over intelligence. And then we kind of punish deviations from gender stereotypes. And that starts as young as infancy. We see, if you go into a toy store, toys are divided by boys and girls' toys. Girls' stuff is going to be pink and purple. Boys' stuff is going to be bright colors and bolder. Typically, this is even arbitrary separations by gender. We start separating kids out in early school, and we have boys line up in one line and girls line up in another. And then as people age, we even have those expectations. We expect men to be CEOs and CFOs, and we expect women to be teachers and nurses. And when people deviate from that, we often don't respond well to it. And then we also have these like weird kind of subcategories for them. One example of that is I have a friend, and he is a nurse in a hospital, and he is often referred to as a male nurse. He's not just a nurse. We have women doctors, male nurses, because there's some sort of deviation from what our expectation of that role and the gender that fills that role should be. All right. So if told that boys don't cry, a man is going to feel more or not feel comfortable expressing emotions later in life. And this is kind of what we call gender typing. So children are going to learn a concept of what it means to be a man or a woman, or to be male or female. What happens then is that we internalize those. For example, big boys don't cry gets internalized into a man who doesn't express emotions as an adult. And those, internalizations kind of have a long-term impact. So research has showed that we organize the world based on gender by age 2 or 3, which means that we have already started to internalize what it means to be male and female, man and woman, by the age of 2 or 3, and started to separate things out by that. The problem is that often people don't adopt gender identities that are consistent with what they've learned about the meaning assigned to their sex, and that can be problematic. An example of this is the story of Brian, who was born with male sex organs and was treated as a boy growing up. He imitated the gender role of his dad and other males in his life, but over the course of his life, he came to see himself as a man and continued to engage in masculine behavior, even though he didn't kind of feel that inside, and that creates this sort of it's a phrase you're probably familiar with, cognitive dissonance, and people then start to struggle with I don't feel whole and I don't feel complete because I only engage in masculine behavior because I have male sex organs, and maybe I am a more sensitive person or a more emotional person, and I just don't know how to express that. Okay, so let's talk about some comparisons between genders. This comic, or this meme here, says that gender we're going to use it in response to genders. He says that it's the same as the ratio of unicorns and leprechauns. So kind of a silly thing, but basically genders are almost identical with a few exceptions to that. So one of those exceptions is aggression. Males tend to be more physically aggressive than females, and that's kind of a worldwide thing. However, females tend to be more verbally aggressive. So if you think about things like gossip as verbal aggression, females tend to be higher in that. Worldwide, males are higher in social power, which means that they tend to be more directive and dominant, whereas women tend to be more democratic and supportive. When it comes to social connectedness, worldwide, boys play to be active and compete, whereas girls generally tend to be in smaller groups with less competition. However, what we have found is that kind of across cultures, around age 50, those gender differences tend to subside and go away. And the difference between men and women is not nearly as large. I like this comic here. You got two different people, and the first one says, do you prefer trans? Because I'm not sure how to pronounce the asterisk. Or is it transvestite? Is that better? How about transgendered person? Trans woman? Trans man? Transosaurus Rex? I'm just kidding. Sorry, I just don't know what to call you. Speed round, transsexual, trans... Sandy works. Sandy. Gotcha. We've been talking a lot about males and females, men and women, masculine and feminine, but what about people who live beyond the gender binary? Remember, gender identifies and helps us express these ways that we typically match with our biological sex, but they're really not associated. They're two independent processes. So what happens when somebody's assigned a male sex at birth, but over time comes to recognize themselves as a woman? These are four trans people. You might recognize them. We have Lana Wachowski. She's the director of the movie The Matrix. Cloud Atlas 5, or Cloud Atlas V for Vendetta. Jenna Talikova was Miss Universe Canada. Chaz Bono was Sonny and Cher's son, and Laverne Cox from Orange is the New Black. You might recognize all of these people. They're all trans people. Some of them you might not have even known were trans because they have changed their body appearance to be more congruent or to match up more with their gender identity and expression. So we're going to end here with a video that's kind of a spoken word about what it means to be a trans person who was raised in kind of a conservative religious environment, and how that plays out and the thoughts that go behind that, because it's hard on those people. So when this presentation is done, I am going to ask you to go to the discussion question and answer a question actually about the brain, and everybody can comment on it, and you will get your attendance credit for watching this and all the way to the end and making your comment in the discussion section. So I hope you enjoy the video, and I will see you at class on Monday.
The first time I uttered a prayer was in a glass-stained cathedral. I was kneeling long after the congregation was on its feet, dipped both hands into holy water, traced the Trinity across my chest, my tiny body drooping like a question mark all over the wooden pew. I asked Jesus to fix me. And when he did not answer, I befriended silence in the hopes that my sin would burn and salt, my mouth would dissolve like sugar on tongue, but shame lingered as an aftertaste. In an attempt to reintroduce me to sanctity, my mother told me of the miracle I was, said I could grow up to be anything I want. I decided to be a boy. It was cute. I had snapback, toothless grin, used skin knees as street cred, played hide and seek with what was left of my girl. I was it, the winner to a game the other kids couldn't play. I was the mystery of an anatomy, a question asked but not answered, tight roping between awkward boy and apologetic girl. And when I turned 12, the boy phase wasn't deemed cute anymore. It was met with nostalgic aunts who missed seeing my knees in the shadow of skirts, who reminded me that my kind of attitude would never bring a husband home, that I exist for heterosexual marriage and childbearing, and I swallowed their insults along with their slurs. Naturally, I did not come out of the closet. The kids at my school opened it without my permission, called me by a name I did not recognize, said lesbian, but I was more boy than girl, more Ken than Bobby. It had nothing to do with hating my body. I just love it enough to let it go. I treat it like a house, and when your house is falling apart, you do not evacuate. You make it comfortable enough to house all your insides. You make it pretty enough to invite guests over. You make the floorboards strong enough to stand on. My mother fears I have named myself after fading things, as she counts the echoes left behind by Maya Hall, Leela Alcon, Blake Brockington. She fears that I'll die without a whisper, that I will turn into what a shame conversations at the bus stop. She claims I've turned myself into a mausoleum, that I am walking casket. News headlines has turned my identity into a spectacle. Bruce Jenner on everyone's lips, while the brutality of living in this body becomes an asterisk at the bottom of equality pages. No one ever thinks of us as human, because we are more ghost than flesh, because people fear that my gender expression is a trick, that it exists to be perverse, that it ensnares them without their consent, that my body is a feast for their eyes and hands, and once they have fed off my queer, they'll regurgitate all the parts they did not like. They'll put me back into the closet, hang me with all their other skeletons. I will be the best attraction. Can you see how easy it is to talk people into coffins, to misspell their names on gravestones, and people still wonder while there are boys rotting their girl away in high school hallways. They're afraid of becoming another hashtag in a second, afraid of classroom discussions becoming like Judgment Day. And now, Oncoming traffic is embracing more transgender children than parents. I wonder how long it will be before the trans suicide notes start to feel redundant, before we realize that our bodies become lessons about sin way before we learn how to love them. Like God didn't save all this breath and mercy, like my blood is not the wine that washed over Jesus' feet. My prayers are now getting stuck in my throat. Maybe I am finally fixed. Maybe I just don't care. Maybe God finally listened to my prayers. Thank you.